signing of a letter contract on 14 January for the fabrication of 16 XSM-65 flight test vehicles, the Atlas program entered a new phase at Convair. Other contract items provide for the construction of a full-scale missile mock-up, the continuation of the missile body development, and nose cone research programs launched by the previous contract, and the expansion of component test laboratories and missile systems development facilities. In anticipation of the program acceleration under the new contract, an Atlas Planning Center was established earlier in the manufacturing facility. Here, advanced production planning was started, and detailed sequencing and scheduling worked out with the aid of numerous charts and this assembly line scale model. Factory space was allocated for the fabrication of the 16 test vehicles, and the space was cleared for the installation of new tooling and the proofing of these tools. The full-scale missile mock-up ordered by the contract was begun immediately, and by early March, design and construction were well along toward completion for the engineering development inspection scheduled for May. The test vehicle being mocked up is the XSM-65 Series A. It is designed primarily to provide data on two-engine booster propulsion performance in flight, but it incorporates numerous other design features for the operational missile for flight testing at the same time. The nose, however, will not be separable in flight as in the tactical weapon. The propulsion system of this engine test vehicle, or ETV, will be unstaged and will consist of two of these North American turbo-rocket engines gimbal-mounted in a non-jettisonable skirt. The experimental missile will be 75 feet long and 10 feet in diameter, and will weigh 182,000 pounds at launching, of which 171,600 pounds will be JP4 fuel and liquid oxygen, or LOX. These propellants are carried in two pressurized integral tandem tanks that form the main structure of the missile body. In developing this thin-walled stainless steel monocoque structure, a ground test article called the Model 7-4 was built under the previous contract. In January, it was cycled for the determination of its vibration modes and frequencies in the horizontal fixture at the special test site on Point Loma in San Diego. A structural steel dummy of the missile body was erected in the test tower at Point Loma for proofing of erection fittings and gear. The pressurized test article was then remounted in its special handling trailer and transferred to the test tower, where it was installed in February. Vertical pressure tests were conducted by filling both propellant tanks with water to determine vertical load and fluid flow characteristics. A vortexing study was made by remote control camera as the tanks were filled through the propellant filling connections. At the same time, a temporary test fixture was built at the Point Loma site for the preliminary investigation of LOX geysering characteristics. These tests were run in March, with the LOX refrigerated by liquid nitrogen. Back at the factory, the construction of the first of several body component test sections was begun. Here, the ellipsoidal bulkhead that separates the fuel and oxidizer tanks of the missile is heliarc welded in a special welding fixture. The bulkhead sections, or gores, are .020 gauge, half-hard stainless steel. The butt seams will be reinforced on the concave side by spot-welded doublers. The test bulkhead will be installed in a special 20-foot tank section to prove its structural integrity under various differential pressure loadings. In the engineering test yard, meanwhile, tests were being conducted on the special fitting that will separate the missile body and the booster unit in the staged Series B and C versions of the flight test vehicle. Several of these explosive-type fittings around the periphery of the booster unit will be fired simultaneously by the flight programmer. A retracting version of the mechanism will separate the nose from the body of the operational missile without disturbing the nose dynamics. When the separated nose, containing the warhead, re-enters the Earth's atmosphere at a speed of about 14,000 knots, it will encounter aerodynamic heating of destructive proportions. It is to develop a means of protecting the nose against this destructive heating that Convair was authorized to continue its nose cone research program. With such special laboratory tools as this hydrogen-oxygen wind tunnel, solid heat sink specimens like this copper cone are subjected to stream velocities of 5,000 knots at temperatures of 4,500 degrees Fahrenheit. A larger hydrogen-oxygen tunnel, now under test, will produce stream velocities up to 6,500 knots and specimen surface temperatures to 6,000 degrees. Other special tools for this research include this 450 ampere arc heating apparatus and this 120 kilowatt resistance heating unit, which has produced temperatures in dense graphite as high as 6,500 degrees Fahrenheit and comparable temperatures in copper and molybdenum. Both of these test rigs, as well as this 20 kilowatt induction heater and these 120-inch and 60-inch solar furnaces, are also used at Convair to investigate transpiration cooling techniques as an alternative to both melting and non-melting solid heat sinks. In transpiration cooling, water or other fluid is forced under pressure into the pores of a porous metal skin, where it is converted by the surface heating into superheated steam, which carries off the heat into the atmosphere. The steam also acts as an insulation layer between the hot boundary layer and the cool skin. To study the behavior of the boiling fluid in the pores of the metal, a single-pore capillary tube is heated electrically while water is forced through it. By measuring the water pressure and flow rate, the electrical power input, and the temperature history along the tube with this thermocouple network, the heat transfer profile can be analyzed graphically for various pore sizes. This .025 diameter pore is now emitting superheated steam at a heat transfer rate equivalent to the maximum required in porous metal. Convair Laboratories, some of the missile system components have been undergoing rating and calibration tests. Here, the primary power battery and inverter prototypes of the electrical system are being checked for power and temperature ratings. The experimental battery has delivered 200 amperes at 28 volts for periods up to 15 minutes in several tests. 160 amperes are used to drive the DC to AC inverter, and the balance of the battery capacity will be available for the DC power requirements of the missile. When these tests have been completed, the units will be installed in their canisters and the automatic temperature regulation system checked out. Later, these and all other system components for the missiles will be vibration tested on shakers like these. 10 such shakers of various capacities, along with their control panels and power supplies, will be housed in a new Atlas Vibration Laboratory. Another laboratory will house a unique centrifuge facility called CVAT for combined environmental vibration and temperature testing of Atlas missile system components under various G loads. Each complete system, such as the autopilot and electrical systems, will be separately and jointly proved in under operational conditions during full thrust, full duration, captive firing runs of the completed missiles in this special Missile Systems Development Stand proposed for an isolated location in Sycamore Canyon on the Camp Elliott Military Reservation near San Diego. Soil analysis of the site has been completed, and the detailed design of the facility is now in progress. These are but a few of the many planning, engineering, and production activities in progress on the Atlas project at Convair. All are directed to a single objective: to add the SM-65 intercontinental ballistic missile to the United States Air Force arsenal at the earliest practical date.